Hello everyone, today we will continue our discussion and today's lecture will be lecture 34 and we will start discussion on oxidation of metals. So, lecture 34. So, topic oxidation of metals and alloys. Now, when we talk about oxidation of metals and alloys, we will concentrate as well as confine our discussion on gaseous oxidation of metals and alloys in presence of oxygen only. Of course, of metal in presence of steam as well as if there is a possibility of CO2 presence, then also oxidation of metal can happen. But we will talk about metal reacting with gaseous oxygen and then forming metal oxide, that particular part we will talk. Now, when we talk about oxidation, from our knowledge in corrosion, we have seen that oxidation means when a metal leaves electron and goes to ions, and it is in basically the aqueous medium where for example, zinc in HCl solution, zinc goes into solution in the form of ions because oxidation of zinc takes place, and we say that zinc minus 2E, it goes to zinc plus plus. This is oxidation or anodic process. Of course, in order to maintain neutrality, these electrons which are released by zinc must be consumed by some cathodic process, which could be hydrogen evolution reaction or oxygen reduction or water reduction. Even there could be possibility of metal ion reduction, like Fe plus 3 plus electron goes to Fe plus 2. So, we have seen that the counteracting cathodic process would be H2 or H2O plus 2E equal to H2 plus 2 OH minus. There could be involvement of oxygen. It can happen like this, or oxygen plus 4H plus 4E equal to 2 H2O, and there could be process like Fe plus 3 plus E equal to Fe plus 2. So, this entire process are cathodic or reduction process. In case of gaseous oxidation, like if I take a metal like iron, if I take it to high temperature in presence of oxygen, then iron can react with oxygen and form FeO or Fe2O3, or there could be a formation of Fe3O4. Then if copper I take it to high temperature in presence of oxygen, it can react with oxygen and form Cu2O or CuO, cuprous as well as cupric oxide. Zirconium, it can form zirconium oxide ZrO2, titanium it can form titanium O2, or aluminum it can react and form Al2O3. So, those are oxidation. If you see that a particular process like Fe plus O2, it goes to FeO, then if I try to see if their oxidation number is 0 now, but when it forms and if I balance it, so balance would be like this. That case I could see that oxygen goes to O2 minus and iron goes to Fe2 plus. Here also you could see that Fe is releasing 2 electron and forming 2 plus, and oxygen accepts 2 electron and forming O2 minus. So, that means here also in case of corrosion, this entire process we are talking about corrosion perspective, where zinc dissolution happens at room temperature and ambient temperature in HCl medium, where I can have oxygen presence in the form of dissolved oxygen, or I can have ferric ion in the form of impurity, and then this could be your only anodic process, and all those reactions can happen depending on the pH of the solution. Now, in the gaseous oxygen, so that means this reaction is iron piece is heated in presence of oxygen, and I could say that this is a dry oxygen. So, then I can have this reaction. So, there also I could see this is oxidation or anodic process, and this is reduction or cathodic process, and this counter balancing oxidation and reduction processes are required to neutralize these charges. Now, in this corrosion case, we are very clear that on the surface of zinc, this is zinc surface, I can have plus E equal to H, this cathodic process. So, this electron comes from a place where zinc goes in the form of zinc plus plus, zinc plus plus. So, this place we have dissolution and this place we have cathodic reaction, and electrolyte is basically acting as a medium where zinc ion is going as well as hydrogen ion is flowing or migrating. At the same time, electrolyte is acting as a charge carrier in the form of ions. But if you see this electron, 2 electron is coming through the zinc piece. So, this is the zinc piece. So, this acts as conductor for electron transfer. Fine. So, that means that is what this is, an electrochemical process where we have 4 components: cathodic or reduction reaction, 2 its anodic or oxidation reaction, presence of an electrolyte, 4th is presence of a conductor, where this migrates, charge migration happens here, and here electron transfer. So, we have 4 components of this corrosion cell or galvanic cell, or even if we consider electrolytic cell, there also we have these 4 components. but here I could see two components, one is this, another one is this. Now, where are the other two components? These two components we have to find out. Now, this is one query we have, that can we consider this oxidation process iron in oxygen as corrosion process, or I can say corrosion or electrochemical process. So, we have to answer this particular query. But at least one thing is clear, that we could see two components, two parts of, if we see this 4 parts, at least 2 parts are there. So, we have to find out 2 more parts. In order to find out, we have to understand how oxidation takes place. So, before we go to that condition, that to that particular query, that how oxidation takes place, we need to know that this is one way of formation of oxide. There could be formation of oxide in the presence of water or steam. So, any metal, if I consider M, it can react with O2, it can form AMXOY, where I can write it as this would be then half y and x. So, this is the balanced condition. For example, if I consider M2O3, that case oxygen would be half into 3 plus 2 m. So, it will become 4 m plus 6 O2, sorry, it will be 3 O2 equal to 2 M2 O3. So, that way we can, so this is a basically generalized formula. M2 M can react with H2O, this is reaction with oxygen, I could say dry oxygen. Then if there is moisture, then that can also react AMXOY plus H2, it can form H2. So, that time I can say that this becomes, so this will be the balance. So, this is 1, this is 2. It can also have oxidation like M plus CO2 then it can form CO. So, I can balance it like Y, Y, then you see that it is balanced. Okay, so this is balanced now, and now here if I put x, this x, y, these are the integers. So, these 3 ways I can see that the same metal oxides are forming, but our concentration would be on this particular reaction. Now, if I try to now understand the mechanism of this reaction, or not mechanism, I would say that what are the different processes that happen when oxidation takes place. Okay. So, that we can see in a little while, but if you see that this FeO formation, metal oxide formation, this oxide formation is a natural process. Why it is a natural process? We know that there is a factor called del G at a constant pressure temperature if that is less than 0 for a particular process. We call it, this is a spontaneous process. Spontaneous process. So, this oxidation reactions what we have shown here, these are having del G, which is free energy change, negative. So, that means those are spontaneous process. If those are spontaneous process, that means those are natural process. Of course, this del G value for different process, if it is iron going to FeO, iron going to Fe2O3 after reacting with oxygen, or aluminum going to Al2O3 after reacting with oxygen, all those processes might have a different values of del G. For example, in case of aluminum plus O2 equal to Al2O3, if I try to see that. So, this is 3, this is 4, this is 2, this is the balanced equation. That case, if I try to see delta G 0, that means the standard state, that means the pressure to be kept as 1 atmosphere, that time this value would be highly negative as compared to Fe plus O2 equal to FeO. So, that means this becomes 2, this is the balance. Here delta Z0 T, if I try to see the same temperature, these two processes are compared. So, this will be negative. I am just putting a comparative statement. We will see later on with the help of Illingham diagram that time we will be able to see the actual values of delta Z0 T, that means the temperature where that oxidation is taking place would be very highly negative for this case as compared to iron oxidation to FeO. So, that time we can say that aluminum has got a very high affinity to oxygen as compared to iron. So, that means if we keep iron and aluminum at a particular temperature in presence of oxygen containing 1 atmosphere pressure oxygen, then aluminum would try to get oxidized quickly, because it has a very high tendency to get oxidized, because its free energy change for the oxidation is highly negative. So, that comparison will come later on when we talk about Illingham diagram, but at least we can see that this oxidation, gaseous oxidation, is a spontaneous process. So, when we talk about spontaneous process, that means we have to also experience oxidation of structural components which are used at a high temperature. Now, this oxidation of structural components at high temperature will not be desired situation, because for example, if I have to design a material for turbine blade application, then that particular blade material must have a high oxidation resistance, otherwise it will keep forming oxides on the surface, and that oxide would lead to degrade its mechanical integrity. It can reduce its mechanical strength, it can reduce its creep resistance, it can reduce its fatigue properties. All those mechanical properties will be negatively affected. Fine. So, that means the oxidation, since we cannot avoid it, we have to find out something so that we can control it, we can reduce the oxidation. So, it is the same way like corrosion. Corrosion cannot be stopped, even oxidation cannot be also stopped, but at least we can do something so that oxidation can be reduced to a great extent, so that that particular material can serve for a longer duration of time. So, that means we have to study oxidation behavior of metals and alloys. Similarly, this oxidation is one part is it leads to problem for the metal which is trying to give service at a high temperature like turbine blades. There could be issues in heat exchanger. For example, sometime in case of chemical industries, we have methane. So, that methane generation, methane can be burned and that methane, instead of leaving it to the environment, we can burn that methane and then we can get that heat recovered in the form of heating steam. So, the steam goes through a pipeline and those are called heat exchangers. So, those pipelines, so you have it is a kind of, you have a chamber, you have a big chamber like this, So, where from you have those flue gases, we call it flue gas, that gas is coming, this is burnt, and now here you have a series stacks of pipes. These pipes are there. Okay. So, now it is connected, one end is entry, another one it exit, entry and then exit. So, through this pipe we are sending steam. So, now when this flue gas is burned, it goes through this particular stacks of pipelines. Now, that process, this heat is then transferred to the steam, fine. So, that way we are actually getting back useful heat by heating the steam. That heated steam can be used in other applications. Now, these pipes are made of irons, made of steel. Okay. So, this or cupronickel pipes, those pipes can also get oxidized, because when steam is moving through this, outside surface might not get oxidized to a great extent, but inside wall might get oxidized to a great extent. Now, if you have a wall thickness of, let us say, if let us say the pipe wall thickness is 4 millimeter. So, this is let us say 4 millimeter, this is the pipe through which steam is flowing, fine. So, now internally we have steam flowing. So, the steam can react with iron and form oxides, and these oxides will form inside wall, and then gradually this oxide will eat away the metal part. So, the actual metal segment is thinned down, and this steam is also said has got some extra positive pressure. So, that pressure might fracture or rupture this outer wall when this wall thickness reduces. So, that time this rupture can happen in the form of fish mouth kind of fracture. So, if you see a fish, that when it opens the mouth, that time it looks like this. So, that kind of fracture can happen of that particular pipeline. Once that fracture happens, then this plant needs to be shut down, because the purpose is not solved, because the superheated steam is actually going along with the flue gas. So, now this happens because of the severe oxidation of the inner wall. So, this is the problem. So, that means we could see that whenever some material is chosen, for example, in case of aerospace applications. Now, copper alloys are used for making combustion chambers, fine. So, that alloy must possess sufficient oxidation resistance or resistance to the chemical or the fuel that is being burnt over there. Otherwise, oxidation can lead to failure of that particular combustion chamber. Similarly, in many other cases, we need high temperature applications. Even for example, thermal power plant, we need application where high temperature is experienced. Even furnaces, if you see induction furnace, if you see any other furnaces, so the outer wall is made of metals, steels, and the inner wall we always cover with refractories, so that the outer wall does not get much of heat, but even if it gets heated, oxidation can happen but that material gives a sufficient oxidation resistance, so that that furnace wall can withstand the load that is there inside. So, that way oxidation needs to be studied, and it is an important aspects of material choice. Like for example, if you have to select material at high temperature, you have to have oxidation properties of that particular metal. So, that way oxidation is an important aspects to analyze. Now, coming to the processes that could happen on the on the metal surface, we can have a series of processes. Like we can have oxygen. When the metal is exposed to oxygen, oxygen can get absorbed on the surface. There could be nucleation of, and then it will be followed by nucleation of metal oxides, and then the coverage of the metal oxide film by a metal oxide film over the metal surface. There could be diffusion of atomic oxygen, there could be dissolution of atomic oxygen with the metal, and then once that limit of solubility of that atomic oxygen in that particular metal exceeds, there could be internal oxidation. Now, oxide might have a different thermal expansion coefficient rather than as compared to the metal. At a high temperature, oxide can crack, it can form micro crack, it can form macro cracks, and then accordingly we will have a difference in oxidation tendency of different metals. So, we will talk about different stages of oxidation in our subsequent lectures. So, let me stop here. Thank you very much.